Okay, so this is video 3 in exercise 8 of chapter 4 of the Advanced GIS textbook. And in this video, we are going to be looking at how census metrics and social vulnerability and social well-being relate to environmental hazards and natural hazards. And so I've got a few different things pulled up here on the screen. The first, if we zoom out to the entire state of Utah, you can see that there's a lot of these lines. These are quaternary active faults in Utah. And I have selected those faults that are within Utah County block group areas and exported them as faults in Utah County. So I could turn the other ones on, and those are shown here in red. Similarly, I have pulled up Department of Environmental Quality air emission inventory sites for the state. And so we want to look at those just in Utah County as well for this analysis. So we can do not select by attributes, but similar to what I did before, Utah select by location and emission inventory sites that are within, completely within, seems fine. Utah County block group areas, apply. And that's selected all those sites. Now there are a lot close to the edge, so you could have added a buffer in there just in case you want to look at those ones as well. But for this purpose, I won't. Then I would export those features to their own thing as DAQ, air emission, Utah County sites. And that can turn off the other ones. So now we've got the block group data in the background, faults in red, and these air emission sites as dots. What we're showing right now in the background is a principal component analysis, just looking at the first principal component of vulnerability. So that's a mixture of PCA of things like percent poverty, percent low educational attainment, percent dependency, first principal component of that. And so it's supposed to be capturing areas of relatively high social vulnerability in the county. Conversely, I made another map here, which is showing well-being. So these are areas of relative well-being in blue, and less well off in brown. And those are using metrics that are things that are positive attributes like high educational attainment, young housing stock, which wouldn't be vulnerable to earthquakes, a high percentage of working adults, a less dependency rather, and other things like that. And so these two things, PCA well-being and PCA vulnerability, show similar things, slightly different patterns, because one of them is looking at metrics that are kind of negative associations, the other is looking at positive associations only and not intermingling the two. Okay, so we'll look at both of those in addition to the input things, such as this one's showing where housing is in a good state. So probably better to show it this way, right? So maybe we want to, yeah, one directional stretch. So the housing good, so housing poor would be on the low side, so that would be old. But we're just looking at areas of young housing here. So I guess, in this case, that would be more of the lighter colors. And so all of those individual metrics from the census were brought in and used in those vulnerability analyses. So I'm going to put the good attributes, and there were 6 of those below the PCA well-being where they're at, and then move the vulnerability ones above the well-being one to here, just for that kind of organization. Okay. And so, yeah, so we can look at those inputs as well. And you'll notice between video 2 and this video, video 3, I have removed the large block groups, which were kind of in the more rural settings, and have just focused on the urban and suburbanizing areas of Utah County, as, not to kind of because especially when we're using this rasterization of the block groups, those rural areas would become overwhelming in terms of the number of pixels with those rural attributes, when they're not actually representing many people. And so we kind of want to look at similarly sized block groups, and so we kind of trim it down. Also, some of those block groups that were really large actually are just parts of the county that are unoccupied, like Utah Lake, and that was throwing zeros into the analysis and skewing the results as well. And so keep that in mind as you're running your analyses. Okay, so the way we want to relate these hazards, so the air emission sites, I'm going to remove the things that we're not looking at. So the air emission sites and the faults, we want to run some buffers. We'll create features, which will be buffers around those hazards, to represent air zones of risk. In the case of air emissions, those zones of risk, would in reality be asymmetric, right? Winds have a prevailing kind of westerly to easterly, west to east flow, because we're in the zone of westerlies. And so we would expect like the pollution to go more towards the east of these zones. But we're going to run symmetrical buffers, just for simplicity's sake here, and but realize that there's an issue with that. And then with the faults, buffers also make sense because, first of all, those fault lines are mapped at a fairly coarse scale. So, and then they're just representations of where the ground's broken in the last couple of earthquakes. Doesn't mean couldn't break somewhere slightly differently near the surface, within the zone of a buffer around the known active fault. Also, those areas are usually sites where extra kind of precaution needs to be taking place as homes are being developed. And some of these areas have already been developed and could have maybe missed some faults early on when we didn't know where the faults were early in kind of the development of this valley. And so having some buffers around the faults makes sense for considering that hazard as well. And so we'll go to geoprocessing and we'll look at the buffering tools, see how we do that. Create buffers, buffer. I usually use this, I guess, but there's this pairwise buffer tool, which is enhanced functionality and performance. We should probably try that. Okay, so let's start with the air emission sites in Utah County. And we can buffer these at a couple of different scales. So we will, in this case, let's buffer by, let's do miles, or no, let's do kilometers. I'm kind of used to kilometers, but you could use a different buffer. So we could say, let's see who lives within half a kilometer of these sites, okay? And and dissolve. So that will be no dissolve, an individual buffer for each feature. Dissolve to a single feature will treat them all the same in case of overlaps. I think we're going to use dissolve just to make to a single feature. Because then we can look generally over the whole area. We're not treating each one. We're not interested in examining each site. We just want to look at the average trend for this analysis. Okay, so we'll run that buffer. Oh, there it is. Okay, and if we look in that pairwise buffers attribute table, yeah, we see one feature and the total number of square meters that it occupies over the area, but there's and there are some overlaps, right? So we're not double penalizing these areas of overlap by making a single feature. Okay, so that's a half kilometer. Let's look also 1 kilometer, so a little bit further out. And I should have named this properly. This first one I ran should have been 0.5 kilometer. And this, so I'll do better this time. And I will say this is 1 kilometer. And I'll run that. Okay, so now we have 2 buffer distances. And just to, so we're going to run some analyses where we see what is the demographic information within that kilometer. But maybe what we really want to know is what's the demographic information in the half kilometer between the edge of the inner buffer and that outer buffer. And if that's true, we can kind of cut them, right? So that's probably not the right term. Right. So there's some different terms for this, so gotta be careful here. So basically, give me just a second. So I'm forgetting the term and I needed to look it up. So cutting features within other GIS, of course. Erase, that's what we want. Okay. So we want the erase tool. Okay, so we're going to input then the 1 kilometer feature, pairwise erase. And we want to erase, so input feature, the features will be used to erase coincident features in the input. And so this would get the 1 kilometer or 0.5 to 1 kilometer. Okay, so this will make like a donut buffer. Let's see if that works. I don't think it likes the 0.5. it only accepted it before because that was a pseudonym that I gave it. Okay, so let's turn off these other ones. And yeah, so you can see that that new one, 0, 5 to 1, is a donut. Okay, so really we're going to use, and let's make that donut color be, I don't know, we'll make it gray, and the other one internal is blue. Okay, so now we can see that we got two different buffer sets there. And we can do the same thing if we go back to our buffer, pairwise buffer is what we really want, right? And if we input the faults in Utah County, and we're going to now do a buffer of who lives within, in this case, we'll just do within 1 kilometer, and I'm not going to do a pairwise. I'm not going to do a donut version. So 1 kilometer, and we do want to dissolve into a single feature. Okay, so there's within 1 kilometer of the faults. Okay, so now we have these features, these buffer features that we want to use. I'm going to drag this one down here because I don't want to use that one. So I have 3 different buffers that I want to look at, the demographics. And so the way to do this is to go into zonal statistics. So if we go zonal statistics, so the input the raster or feature zone data that we are going to go after, right? So if we wanted to know, if we wanted to go to the PCA, what's wrong with that? Oh, the feature zone data. Sorry, I'm going the wrong direction. The input raster value. Okay, so the buffer is what we want here. Students and I often get this confused. So you can use zonal statistics as on rasters or features. And actually, I've gone to the wrong thing. So we actually want zonal statistics as a table that we could then append to the feature data. Okay. And so if we then input faults Utah County 1 kilometer, and there's only, it's a single feature that we're looking at here. And if we then input, let's just input, PCA vulnerability, that's gonna, I believe, use the value. Well, that's going to be a little bit hard to understand. So actually, let's look at look at higher education professionals, or professional degrees. So this is like master's, business, law degrees. We're going to look at the statistics of that in look at the mean, and we'll ignore no data in the calculations. We're going to output that as zonal stats fault high ed. Okay, so we'll run that. And it's just really simple. If we open this up, it's going to tell us that on average, 16% of people within that 1 kilometer of the faults have graduate degrees, basically, is what that's saying. If we look at then the general data for that, if we go to the symbology and the histogram of that and look at show statistics, on average within block group pixels across the area, it's 14% have graduate degrees. And so within 1 kilometer of the fault, it is 2% higher, is what that's telling us. Okay. So we could do this again. What might be an interesting thing to look at would be, well, where are the old homes, maybe? Okay. And so now we'll call it zonal statistics, faults, old home house. Can run that. So on average, 27.7% of the homes are old stock, meaning that they probably don't have good earthquake considerations in their design. How does that relate to on average? So if we look at old homes, symbology, histogram, show statistics, on average, it's more like 22%. So there are more old homes in on average within those fault zone areas across the overall area. So that's a concern for vulnerability. Let's try for the overall. Well, let's look at minority actually. So faults and minorities. Let's see what that looks like. So 18% of people are minorities within those fault areas. How does that compare to Utah County as a whole? Go to the histogram, statistics. It's on average 19%, so it's about typical. Okay, so nothing, not too bad, right? Now we'll do two more. We'll go to looking at the for PCA vulnerability, and we'll call this fault vulnerability, because this PCA is supposed to be capturing a bunch of things, right? And so the number might not, it's not a percentage exactly, but you can see, is it above, more vulnerable, or below the average? So the mean is for within the fault zones, 1 kilometer, 0.325. And if we look at PCA vulnerability and go to symbology and go to the histogram, statistics, 0.26. So that's saying that it is a little bit more vulnerable than, right? This is 0.32 as opposed to 0.26 over the whole area. And that probably ties into the old houses that we saw and then kind of other things related to that. And so I was a little surprised because I thought that might be the opposite relationship. But let's also see how it goes with PCA well-being. And so this one called F well-being. So this is supposed to be capturing areas of relative well-being. And that is showing us 1.49. And if we go into well-being, look at the symbology there and the statistics and that. So the mean was 1.54 across the area, and this was 1.49. So it's a little bit lower than average, a little bit less well off than average across the area. And so that's consistent with the vulnerability analysis. So all we've done is look at what are the demographics within this 1 kilometer buffer and compared it to the demographics across the whole area. And so that's pretty simplistic analysis. One way to do it. This next way to do it is to compare, what it is as we move away from the hazard. So we step away. So we can go then to this zonal statistics as a table again, but now we're going to look, we'll look really close in to these hazardous air emission facilities, and we'll look at, let's look at, I guess, minority, and we'll call this zonal statistics 0.5, so 0.5 kilometers minority, and run that. And so 25.7% of the people living in half a kilometer of these hazardous emissions facilities are minorities. And if we remember back to what we were just looking at over the whole area for minorities, we go to the symbology for that, and we went to the histogram, the statistics say that it's 19%. So there's 6% more minorities than on average in those areas. And we can go then back here and try to see what it looks like if we go a little further out. And we call that, I'm just going to call it the 1 kilometer, but it's really this kind of donut. And we'll run it. We open that one up. We see a pretty similar answer, actually. Almost exactly the same, but not quite. Interestingly, it actually goes up a little bit. Okay. So that's not always the case. Sometimes you see that a vulnerable group gets more and more vulnerable as you get closer to the hazard. This case is 1% higher if you step out another half kilometer. Let's look at something else. So if we look at the opposite of minority, but we look at white, I guess that's kind of boring. We'd probably get the opposite answer, right? So let's look instead people in poverty, and we can keep it this 1 kilometer poverty. Run that. And so we see here that it's 8% of people are in poverty in that half half to 1 kilometer buffer area. Generally, if we go to poverty across the area, the statistics for that say that on average 4% of people are living in poverty. So that's twice, you're twice as likely to be in poverty if you live close to those facilities in that half to 1 kilometer range. Let's see what it looks like if we go into the half kilometer again and look at poverty. So zooming in even more. And it's just a similar result, about 8%. Um, so, so yes, so generally speaking, higher rates of poverty near these air emission sites. Um, we could look generally at then the PCA vulnerability, and could do the same thing. That I won't belabor this too much, but in your lab, where you'll be looking at toxic release facilities, you might do this for multiple zones of buffer distance away from sites, um, and look at how uh, that buffer relationship follows these trends. Okay, so let's see how that relates. So if we go to So 0.276, and I've already forgotten, on average, is that more or less vulnerable than the band 1 data set? Okay, so it's slightly more vulnerable. Uh, Now, not a lot more, but slightly more, right? Um, and so, yeah, vulnerability is a factor that's related to multiple things, right? And so we saw that poverty was in important vulnerability, right? The housing cost is going to be lower next to the industrial facilities that might be releasing these toxic chemicals. And so it makes sense that lower income people might be situated there. We might find that other aspects of vulnerability aren't necessarily co-located with some of these hazards. And so zonal statistics is a great tool that we can use to look at how these spatial statistics vary across the region next to these facilities. Um, we've treated all of these buffers as one feature, and so that's not a very nuanced way to go about it. You could, of course, um, treat them individually. You could apply asymmetric buffers, try to capture where the hazard is in a better way. So air currents, or in the case of faults, maybe there's more risk on one side of the fault on the hanging wall side versus the footwall. And so you could apply asymmetrical buffers. Um, but I've shown you how to get the statistical data. You can then append that data uh, to the features if you want to have all of that data in the features and easily accessible, so you can kind of plot how those things change with distance. Um, yeah, and so I hope that you find this useful and will help you in kind of analyzing not only aspects of social vulnerability and features and using buffers, but you could use other things as well. So you could, think about like who has access to maybe facilities that are, really kind of positive aspects in society. So maybe access to public transit, We could look at access to recreational sites and things like that. Yeah. So be creative, and so principal component analyses, buffers, and zonal statistics is a nice kind of nexus of spatial analyst tools that'll enable you to relate these things.